Thanks, Brent. Basically, at this point in time, I just want to remind people of a couple of things. Substantive questions about the presentation anyway, posed in the question and answer box will be answered either directly by panelists at the end of the session after Bruno's talk, or if there isn't time for those to be answered, we will upload the whole question and answer block to eClass, and more questions will be answered in eClass subsequent to the presentation today. I know there was still another question about certificates, so I'll just say again, certificates will be distributed at the end of the entire course. Your participation is recorded as a part of participating in this session. There will be other opportunities to interact in the forums on the eClass site. But for now, let's turn to the second part of our presentation today. And I'd like to introduce Bruno Wichmann, who is an associate professor in the Department of Resource Economics and Environmental Sociology at the University of Alberta. He has received his PhD in economics from the University of Tennessee in Knoxville, USA. He's originally from Brazil. His research interests are primarily in the fields of environmental economics, social and economic networks, and experimental economics. But he's going to be talking today about some of the dynamic interactions between a pandemic such as the COVID-19 and macroeconomic indicators. With that, I will turn it over to Bruno.
Thank you, Ellen. Good afternoon, everyone, and welcome to this course. Thanks for participating. And today, like Ellen just said, I am going to talk about epidemiology and economics. So my presentation will have three parts. The first part, I'm going to talk about economic performance and how economists measure economic performance, economic activity. And then we move on to second part, and we'll talk a little bit about epidemics. And then we'll link in the final part, the first and second parts, I'm going to look at how could an epidemic affect the economy. So we're going to look at a simulation model to see if we can get some insights from a simple simulation. Okay, so let's start with the first part. So how do economists measure economic performance? And, of course, there are several ways to do this, but perhaps the most popular way, the most common way would be production output, GDP. So gross domestic product, which is the total value of all goods and services produced in a country during 1 year. Okay, so if output is what is important for economic activity, then the next question is, what determines production? And one approach to go about this is to look into a production function approach, where output is a function of factors of production. So here I have an example from the agriculture sector, where I have inputs or factors of production such as machinery, tractors, irrigation equipment that altogether is part of a stock of capital of an economy, right? Drones are also being used in agriculture, and labor, like people that work in the agricultural sector, like for instance, here I have a picture of a technician, a drone technician, right? So all these factors of production go into, are mixed into a production function, which is something that incorporates everything that goes into transforming factors of production into outputs. So this is something that we incorporate the productivity of capital, technology, and in some cases even the institutional environment of this economy, okay? And at the end of this, and the other end of this function, we have output, which is our final product. Like here I have a picture of grains that are ready to go to the market, okay? So if production is really something very important, we can then track the evolution of a country over time by tracking the GDP over time, right? So we can track the growth rate of GDP over time. And what I want to show you next is some data from the World Bank on the average growth rate of GDP for the last 30 years. So every year I have an annual growth rate, right? Every year the GDP is growing. So let's get an average of that growth rate for the last 30 years. And when we do that, the world grows just below 3% a year on average. So when we get all countries of the world together and look at the value of that production, it's growing just under 3%. And we have, of course, this is an average. We're going to have countries growing below than an average and faster than average. And the countries that are growing slower than the world many of them are developed countries, like Canada growing at 2.57%, which is a growth rate really similar to the US growth rate. So we have countries like Germany and Japan growing much slower than the world. And we have developing countries like Chile in South America or Ghana in Africa, and Asian countries like Vietnam and China that are growing much, much faster than the world. So economists look at this data, look at the strands, and it's our job to try to make sense of this data and organize this data and see if we can write down a model that can explain these patterns. Why is a country rich? Why is a country poor? Why are some countries going fast and why are some countries going slow? Okay. So one of these models is the solo growth model. It's perhaps the most popular growth model or long-run macroeconomic model out there. And it's a model that describes the evolution over time of factors of production and outputs, okay? So this model is able to deliver differentiated growth rates depending on the stage of economic development. So it does capture this idea that cutting-edge growth is much harder than early development growth. So if I go back to an agriculture example, let's say I have a country or an economy that I have 10 tractors and I want to add a new tractor to my operation, I want to accumulate capital, that's much easier than to add an additional tractor when I already have 1 million tractors, let's say, right? The model captures that and also captures, of course, many other parameters of the economy as a good model would capture, like savings rate, technology. Some versions of the model have human capital accumulation. And this model has been widely applied to the data. It's been shown to explain the path of economic growth of many countries after the World War II. And perhaps one of the very popular paper that shows this is the Mankey-Roman whale paper from the 90s, published in the QJE, the Quarterly Journal of Economics, that get to this result. Okay, so let's take a look at a diagram that kind of summarizes the solo model. And the way I like to think about the solo model is to think of it as two pieces, two parts. And the first piece we already talked about, it's production, right? So we have inputs, and these inputs are combined to generate output. What the solo model does then is to say that, well, not everything that we produce we're going to consume. Some of it's going to be invested, okay? So a share of output is invested. We call that share the savings rate or the investment share. And in Canada, it's 8%, about 8% of our output we are saving. And this investment is going to be channeled back into the inputs. So it's going to allow us to buy new tractors and generate this capital accumulation so that I keep growing my capital stock, okay? What happens when I have more inputs? I produce more, I have more outputs. And then again, we're going to invest more and we're going to accumulate capital more. And this here on the left-hand side of our screen is kind of the engine of growth of the economy and how economies are growing according to the economic model by accumulating inputs and producing more output and investing and keeping this cycle going on, okay? So if you want to see the equations of the simple version of the solo model, we can have the first stop here, production. So here I have a production function with a Copley-Douglas production function. And the more flexible you make this production function, the more sophisticated is your model, okay? So this is a very simple way to do this. And then we have a system of differential equations that explains this motion over time of these variables, like how I'm accumulating capital over time, how is labor growing over time. This is the part that explains the dynamic process in this engine of growth, okay? So let's move to the second part of the talk, and let's talk a little bit about epidemics. So recently, we have been exposed to a lot of technical jargon. Things like flattening the curve, exponential growth, And some news media outlets even post their own simulation models online. And here I have a link of the Washington Post. You can click here and see kind of play around with your own simulation, okay? But one thing that is much less discussed, I think, it's the question of why do economists or scientists use models to begin with, right? And if you ask different scholars this question, you're gonna get different answers. But here's what I think about it, like in a nutshell. So I think that models are a way to translate abstract ideas and thoughts into a precise language, which is math, right? So when I have an idea and I'm building a model, I have to write down equations that are very precise and are telling the channels of how one variable is affecting another variable, which then allows us to experiment, right? So I think of modeling exercise often as an experiment where I can see, well, what happens when I double this variable? What happens to this other variable? What happens if I change my assumption and rewrite this equation in a different way? So this exercise, I'm learning new insights, okay? And then when it comes to epidemiology, one of the most popular models is the SIR model, that stands for Susceptible, Infected, and Recovered model. The idea is very simple. We have a fixed population in the simplest version of the model. We have a fixed population, and every person is going to be in one of three boxes. We have a susceptible box that these will incorporate all the individuals that are healthy and can get infected, but they're healthy. This is pre-infection, okay? If you get infected, then you are moved to the infected box, the second stage of the model. And if once you get better, you're recovered, you move to the final box, the recovery model, and we are assuming here that you get some short-term immunity at least, and then you cannot infect other people, okay? So what the model does is, again, we're going to use a system of differential equations just to explain how people are moving from one box to another box, okay? And one of the most important pieces of the model is that first movement, how healthy people at the speed, right? The speed at which healthy people go from the first box to the second box. And the model is saying that this is proportional to the amount of interaction that susceptibles have with infected people, okay? And this alpha here is the contagion rate. So if this contagion rate is high, people are moving from the susceptible box to the infected box really quickly, okay? If it's low, let's say we are washing our hands, we're practicing social distancing, then we can slow down this movement. And then we have another equation to describe how we go from the infected to recovered. Again, is a constant parameter that says that a proportion of infected people gets better at every time period, okay? Right, so what's the idea now? Why don't we look at the economy and the epidemic in one system? Because look, we have the simple solar model that is described by a system of differential equation. And we also have an epidemiologic model that is described also by a system of differential equations. So why not put these two systems together so that I can kind of see how changes in the epidemic affects the economy using these two simple models. And this is exactly what Sabini and others did in a paper published really recently, December 2019, just a few months ago. They published this paper in Applied Mathematical Sciences. And their idea is to keep the economy part as in the Solow model, but vary the way that the labor supply grows over time, okay? So in the simple Solow model here, I have labor supply growing. So L dot is a notation for how labor is evolving over time, okay? The labor supply evolves over time at a constant rate. So this is capturing the idea of a country that the population is growing at a constant rate. And if the population is growing, the labor force, the workforce is also growing. We're using this labor to produce, okay? Instead of having that, let's say now that labor comes from the epidemiologic model. Let's say that only healthy people can work. Let's say what happens if I have an economy where infected people cannot work? We don't let them, either because they're sick or because we don't let them, okay? So then now the labor supply, the dynamics of the labor supply is gonna be equal to the dynamics of healthy people in the epidemiological model. So I'm not having the I group here, okay? only people that are healthy can work. So either before you get a virus or once you recovered from a virus. All right. So what I want to do for the second half of my presentation is to look at a simulation model, okay, and try to see some insights based on this model of Sabini. But before I do that, let me give you a remark that I'm not an epidemiologist, okay? So the goal of this exercise is not to show you a model that explains what's happening right now with the COVID-19 pandemic. So these simulations that I'm about to show you are based on the simplest versions of these epidemiological models and simplest version of the economic model. So they're not able or not even designed to capture the complex features of the real world. Instead, the idea now is going to be to unpack the modeling exercise scientists do. And now we're going to try to showcase what type of insights simulations can deliver. Okay, so things here are going to be a bit exaggerated so that we can clearly see movement and impacts. But let's start with this first graph. Okay, here I have no epidemic. So I have a certain population size, and here I chose arbitrarily a population of 2 million people, which is more or less the size, a little under the size of Alberta's workforce, okay? So these are a number of people, and this is time. Think of this as a day for now, all right? This is time, so I have a year here. So from day 50, 100, 150, all the way to the end of the year. So if I don't have an epidemic, everyone is my first box of that model, okay? Everyone is susceptible. No one is infected. I don't have an epidemic. So everyone is in that category throughout the year, okay? The exercise that we're gonna do is we're gonna simulate a epidemic, and we're going to then double this epidemic in the sense that I'm going to change one parameter of this epidemic. I'm going to only change the contagion rate of this epidemic. I'm going to double the contagion rate of this epidemic. And we're going to see how things move by doubling this baseline epidemic and see what kind of insights we can get as I go from my small, I'm going to call this a small epidemic, okay, for short. But that means just an epidemic with a given parameter of contagion, and then I double that parameter and I get a large epidemic. The first thing you can see is that here I'm on the small epidemic page model. It takes a while for the epidemic to kick in. Like if you see the orange line is the number of healthy people. If at any given day, when I sum vertically like this, I have to get 2,000, okay? So, sorry, 2 million. So this orange line then is the amount of people in that middle box. So every day, how many people in this economy is infected or carry a virus, for instance. And we can see that the amount of infected people, it takes a long time for the epidemic to kick in this model, right? So we have a lot of flat spot here. You can even see the orange curve. And then around day 100, after 100 days, we started seeing growth, and it's like exponential growth, like really steep growth. We reach a peak at around 150 days, and then we recover, all right? And let's see now how this compares to a large epidemic where everything is the same, but I'm only changing one parameter, the rate of contagion. You can see that things are much more pronounced and happens a lot faster, okay? So let's take a look at the first insight. The first insight here is that doubling the rate of contagion makes the infection peak increase by a factor of 2.6. So I double the rate of contagion and I more than double the infection peak, and by that I mean the day that I have the most number of infected people, okay? So in the small contagion model, I have about 300,000 people infected in this simulation model. And I double the epidemic, and the number of infected people goes up to about 800,000. So it's more than doubling. So things can get exponentially faster, get complicated really fast as we're changing the contagion rate. Okay. Another thing we notice is that if I double the rate of contagion, the economy reaches the peak of infection much faster. It's about a third of the time. So it's much faster. You can see that I get a peak here at day 150. That means that in this day, about 300,000 people in the simulation are going to be potentially needing medical attention and be needing the healthcare system. When I double this epidemic, now I have 800,000 needing the healthcare system after just after 50 days. Like So from 150 to the peak is larger and comes much faster. So you can see that the blue line of healthy people before you get the virus go down drastically. Okay. All right. And then we have site number 3. Doubling the rate of contagion makes 98% of the population infected in the first quarter of the year. And that's very different from when I have it, right? If I have a small contagion, if you look at the blue line, I have about 2 million people, healthy in the beginning. The infection kicks in, people are getting sick, but at the end of the infection runs through and we don't have everyone infected. This is what to expect is going to happen in many countries, right? Not everyone is going to get infected with the COVID-19 virus. In this simulation, about 20% of the population is not infected when I have a small contagion rate. But when I double the contagion rate, everyone's going to get infected. In fact, so fast by just doubling the contagion rate that everyone is infected in the first quarter of the year. 98% is infected in the first quarter of the year. Okay, so the epidemic is way more aggressive. So that's why washing hands and encourage people to wash hands, encourage people to practice social distancing is important because it can help us to go from a large infection, a large epidemic to a small epidemic. And this movement is what people refer to as flattening the curve, okay? We are making the process of going through the epidemic a bit more smooth. All right, so now let's turn off the epidemic and let's bring in the solo growth model, all right? So here's a standard, I have no epidemics. So here's a standard solo growth model. So in this model, I have 2 inputs. I have capital. Here's my stock of capital. And I have labor. Again, we are looking at how things move over time. 2 inputs producing my output. So both inputs are needed. So at any given point in time, I have a certain stock of labor. I have a certain stock of capital. I mix them in a production function, and I generate some output. What's going to happen? Investment. Investment leads to capital accumulation. So from this output here, I go over. So from this 2, I go to output. Output generates investment. I go here and I buy more tractors, right? I increase my stock of capital. We have a model here that labor is fixed. Okay, I'm assuming that labor is fixed in the short term here, but capital is accumulating. Okay, so I'm increasing. So here you can see that the early stage of the capital accumulation process, capital grows much faster, right? It captures a little bit of that idea in the beginning that of developed countries going slower because maybe they are in later stages of accumulation, okay? And the capital is going a bit slower. All right. What we're going to do now is turn on the epidemic. And remember, the assumption here is that if you are infected, so the orange line, so members of the orange line in this epidemic, they are not working anymore. If I have no epidemic, I have the blue line here going across the time period with 2 million people, everyone's working. We're assuming that everyone's working. When I kick in some epidemic, what I'm calling this small epidemic, I have this hump, okay? Which the mirror image is the crisis in the labor market, right? So I have at about 150 days, I had a peak of infections, the peak of unemployment for the small contagion in the labor market. This is a time period here that have least labor employed to produce, okay? And then again, we're gonna double the contagion rate, is gonna see how things change in the economy. And before I look at the insights in the labor market and in the economy, let's take a look at this. Look, it's interesting to see that the epidemic affects the labor market and it's going to affect the entire economy. Everything is interconnected in the solo model, right? Because if I have less labor, I'm producing less. If I'm producing less, I am affecting my capital accumulation, right? Through my investment. So I have an epidemic, I have a direct effect on labor and an indirect effect through the dynamics of the model on capital accumulation process. We'll talk a little bit more about this in a second, okay? But let's now look at some insights from the exercise of looking, when I go from a baseline epidemic, that's a made up epidemic, it's a baseline epidemic, but when I double it, so I have some baseline and I want to mix things, I want to change one parameter, make the contagion twice as high, what are the changes in the labor market? And we have the first insight here, which says that doubling the rate of contagion decreases the duration of the labor market crisis by 34%. So this can be a bit counterintuitive, but let's talk a little bit about this. So The way that the model is designed here, the simplest form of the solo model, it's a full employment model. If I have labor, we're going to use it. Okay, we're going to use everyone that is in the economy and is able to produce. We're going to use it. It's part of our production function. But with a small contagion, I don't have labor in certain days. Like in certain time periods, I don't have labor because people are sick. And by assumption, we are moving sick people from the economy, okay, from the labor market. If you look at the time period, how many time periods I don't have full employment, yeah, that is actually longer than if I had a large contagion. Because in the large contagion, things going through much quicker through the economy. I have a smaller gap. So inside 4 is saying that the duration of the crisis, just the duration, is 34% less compared to the small crisis of the small pandemic. But that could be a misleading thought, right? Because economists like to distinguish a lot between the intensive margin and extensive margin, right? So one thing is how many days I have of a crisis. The other thing is what's the depth of each day. Because of course, 1 day of 10 unemployed people is much better than 1 day of 1 million unemployed people, right? So a better metric to see what's the overall effect on the labor market is to see the number of unemployment as measured by worker day, okay? So overall unemployment over the year, what's happening? And that's inside 5, and it says that doubling the rate of contagion increases overall unemployment by 23%. So I'm doubling the rate of contagion, and so I have some, let's go back here. I have some small contagion, a small epidemic, which is this, and of course I have some unemployment because I'm not at full employment. So this area here would be a measure of the impact of my small epidemic on the labor market. But I want to see what happens when I double this. I want to go from this made up epidemic to twice as bad epidemic, okay? So I have some baseline there to compare. And when I increase the crisis, unemployment increases by 22%. So on top of the original unemployment, I have 22% additional unemployment given the large contagion. So I'm just comparing the areas under the $2 million line curve between this curve and this curve. So the impact is much greater on unemployment, which is an argument to actually slow down. It's actually a pro-economic argument to slow down the contagion rate. So if we actually run through this crisis in a slower way and we flatten the curve, this model is predicting that the overall impact, even though longer, is going to be much smaller on the labor market. All right, so let's now look at output. And if you look, let me turn off the epidemic, and if you look at the long run output, so my end game, where I'm going to be at the end of this time period, and I have some output right here, just over $2.5 million. And when I'm going to turn on this small epidemic, and I want you to focus on the end of this graph, okay? And look, there is a fluctuation, but we kind of go back to where we were, or where the long run equilibrium without the epidemic is. If I turn a large contagion the same way, right? So you get to insight number 6, that in this model, the epidemic does not affect long run output. And here's why looking at the assumptions that you're making is an interesting exercise, and you can learn from it, because the only channel that is working here is morbidity, right? So it's this idea that if I have sick people that are not working, but I'm also assuming that everyone recovers, right? And I have nothing else. It's a very simple model. So while I am in the crisis, the epidemic is really high, people are stopping work, and the stock of labor really decreases. But later increases, the economy picks up again. Interestingly, it picks up at a different level of capital stock. Like, so in the beginning I have a certain level of capital, at the end I have another level of capital, but I go back to the original trajectory, in the long run trajectory. So we recover once the epidemic runs through. That's also not to say that the impact of the epidemic is zero on output. And insight 7 speaks to that. So insight number 7 is saying that doubling the rate of contagion of this epidemic decreases aggregate output by 24%. So I have some made up epidemic here, and I have some output loss. Now I'm looking at this curve, okay? Comparing how much I should have without epidemics and how much I have now. So we're losing some production here. I should be going over here, right? And I'm losing some production here. and I already lose some output, but when I double the rate of contagion, how much more do I lose? And this insight is saying that you lose 24% more, okay? So it's much stronger loss in output when this happens. You can see, of course, then as the crisis is deeper in the economy because I have too fast of contagion, I also have a deeper impact on the capital accumulation. If I look at small contagion, it's a much smoother process than the disruption that happens just as we are about the peak of the infection in capital's markets here, okay? And finally, so the last insight is going to be about this variance. Doubling the rate of contagion increases the variance of output by a factor of 2.6. So it more than doubles the variance again. So I'm doubling one parameter of the epidemiological model, and I am more than doubling the variance of the output. And this variance not calculated as deviations from the mean. It would be kind of around here. That's not a good measure. This is variance in the sense that I'm calculating from deviations from the baseline of no epidemic. Okay, so deviations from where we should be in this model if we didn't have an epidemic. So we have some deviations here, right, going down, and have more deviation here. In fact, when I double epidemic, the insight is saying there are more than double the instability. And even though we're not modeling this directly here in this model, we're not capturing the direct effect of instability on capital accumulation. That's certainly an effect that is possible in real life, right? We don't like unstable economic markets, don't like when things are too unstable, there's high variance, all right? So to summarize the talk, let's just summarize the pathways that we learned from this exercise. So I have an epidemic, and the epidemic affects the labor supply, okay? So remember we saw this in the beginning of the talk. We saw that both capital and labors are important pieces of production. They are combined with technology, with other aspects of the production function to deliver an output. But if I'm decreasing labor, I'm also decreasing output. So a epidemic generates a decreasing labor supply that generates a negative impact on production. And now if you look at the solo model, less output leads to less investment because a share of output is invested. So if I have less output, I'm going to end up having a contraction of investment. So this is this channel now. Have less output, less investment. If I have less investments, I have less resources to buy new tractors to accumulate capital. Okay, so it might be the case that my tractors are breaking, so I'm losing, like, let's say per time period 2 tractors, but I can only buy 1 tractor. So my stock of capital is decreasing, and now I have both inputs going down and making output go down even faster than in the beginning when I only have one input going down, which was labor. Output is going down, investment is going to go down again. Okay, so now this portion that once was the engine of growth of the economy is now this trap, right? Is now the engine is running on reverse. I'm actually decreasing, destroy output. And here I'm talking about this downturn, right? Right here, when the epidemic gets too strong, labor goes down deep, the economy is losing resources, and capital accumulation is losing, generating this hump here in the capital graph. Okay, only when we can get rid of the epidemic, only when the epidemic runs through, again we get the engine of growth working again forward, and capital. Look, then labor is going to be increasing, and capital is going to go back to increasing, and then our output is back to increasing. Okay, so you can see that things like a vaccine that get us up going and decrease, let us go through the epidemic and let's move away and get less people infected, lesser of impact in the labor market, that can definitely help a lot is us to go back to this capital accumulation process and get up to a upward trajectory. And yeah, and this is the end of my program. I'm going to turn the word back to Alan. Let me just figure out how to do that. I'm going to stop sharing. There you go. And I hope you guys enjoyed this part.